Chapter 4, Exponential and Logarithmic Functions, Section 4.1, Exponential Functions. Having studied functions in general in Chapter 2 and polynomial and rational functions in Chapter 3, we now turn to a new family of functions, exponential and logarithmic functions, and we'll begin by introducing in Section 4.1 exponential functions. Then in the following section we'll introduce logarithmic functions, and we'll also see the connection between these two types of functions. We're going to introduce exponential functions by way of an example. Suppose that on the first day of the month you deposit 1 cent in your piggy bank. Then on each day thereafter you double the previous deposit. Let A be the amount you deposit on day X. Find the function a of x. So we'd like to find a function that tells us how much we deposit on any given day. And to see how we might construct such a function, let's look at some deposits for specific days, starting with day 1. So the amount deposited on day 1 would be a of 1. So we would write a of 1 equals, and we're told it's we're going to deposit 1 cent. I'll write that in dollars. 0.01 would be 1 cent. So the deposit on day 1 is 1 cent. The deposit on day 2 would be 2 cents because we're going to double the previous deposit. The deposit on day 3, a of 3, would be double the previous deposit, so that would be 4 cents. Let's do one more. A of 4, the amount deposited on day 4, would be double the previous deposit, so that would be 8 cents. So here we see the amounts deposited on the first 4 days. Now, let me write this in a little bit different form. The first amount is, I'm going to write that as 0.01 times 1. The next one as 0.01 times 2. The next one as 0.01 times 4. And the final one as 0.01 times 8. So you see that the doubling is indicated by the sequence 1, 2, 4, 8. And what we might note is that these numbers are powers of 2. 1 is 2 to the 0 power. 2 is 2 to the first power. 4 is 2 to the second power. And 8 is 2 to the third power. So we can see the pattern is that it's 0.01 times 2 to an exponent, where the exponent is 1 less than the value of x, the day that is. So the function a of x could be written as a of x equals 0.01 times 2 to the x minus 1 power. This is our first example of an exponential function. An exponential function is a function that has an exponential expression where the base is constant and the exponent is variable. Now, to appreciate another aspect of exponential functions, let's look at the next question. How much would you deposit on the last day of the month? That is day 30. Okay, again, note that our function from above is a of x equals 0.01 times 2 to the x minus 1 power. So what is the amount deposited at the end of the month on day 30. According to our function, it would be 0.01 times 2 to the 29th power, because the exponent would be 1 less than the value of x. If we use a calculator, this is the dollar amount. In dollars, it would be 5,368,709.12. So you can see that from starting from very, very small deposits, after only 30 deposits, we're well into the millions of dollars. So obviously you're going to need a rather large piggy bank if you continue this process for a month. But this illustrates how rapid the growth can become with an exponential function. So the function we derived above is classified as an exponential function. An exponential function has a constant base and a variable exponent. When something increases according to such a function, the rate of growth eventually becomes very high, as we demonstrated in answering this last question. In general, a function of the form f of x equals a to the x, where a is a positive constant and a is not equal to 1, is called an exponential function with base a. Now we can actually include a equal to 1 if we wish, but actually what happens in that case is we just get a constant function, the function whose graph is a horizontal line. So usually we don't consider that to be an exponential function. So the base should be a positive number, and we don't usually include 1 as a base. To get a better idea of some of the basic properties of an exponential function, let's graph perhaps the simplest exponential function, which would be f of x equals 2 to the x. That is, a is equal to 2 here. So we're going to raise 2 to different powers. This is rather similar to what we looked at in our introductory example. Let's start actually with the ones that we used in our previous example. So with x equal to 0, we would have 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. For the negative exponents, let me begin with x equal to negative 1. We use the rule that a negative exponent means a reciprocal. So 2 to the negative 1 would give you 1 over 2, or 1/2. 2 to the negative 2 is 1 over 2 to the positive 2. So that would give us 1/4. 2 to the negative 3 would be 1 over 2 to the positive 3, and that would give us 1/8. Now notice all of the y coordinates, all of the y values are positive numbers, even though the x's can be either positive or negative. Let me plot these points now, and then we'll sketch the curve. So let's again begin with the x equal to 0. We have 0, 1, which is a y-intercept, 1, 2, 2, 4, and 3, 8. Then for the negative exponents, at negative 1, 1/2, at negative 2, 1/4, at negative 3, 1/8. So you can see as we move from left to right, each y value is double the previous y value. And I just paused the video and connected the points with a smooth curve, which would be indicated if we plotted additional points in between the ones that we already plotted. And we're not taking into consideration how we would interpret 2 to various in-between values of x, such as 2 to the 1/2. Well, for example, 2 to the 1/2 would be the square root of 2. But actually, we can define powers of 2 or powers of any positive base really for any real number exponent we wish. And there's a way that you can interpret that. I'm not going to go into the details, but basically the domain of the function is a set of all real numbers. We can use any exponent we wish. So note the difference between the exponential function f of x equals 2 to the x and a simple polynomial function like g of x equals x squared. The exponential function has a constant base and a variable exponent, while the polynomial function has a variable base and a constant exponent. So notice that in the case of the exponential function, the base is constant, whereas in the simple polynomial function, the base is variable. On the other hand, with the exponential function, the exponent is variable, while with the polynomial function, the exponent is constant. We also noticed in our introductory example how fast the exponential function grew. Note that f of x equals 2 to the x grows faster than g of x equals x squared. In fact, it eventually grows faster than g of x equals x to the n for any natural number n. So even if you used a larger exponent for the polynomial function, eventually the exponential function 2 to the x would grow faster than the polynomial would. So exponential growth is much faster than polynomial growth. Now the graph of f of x equals 2 to the x illustrates some general properties of exponential functions that we will now list. The domain is the set of all real numbers, as I was mentioning a moment ago. And the range is the positive real numbers. So the domain is minus infinity to infinity. The range is 0 to infinity, not including 0. And you can see the range is illustrated in the fact that the graph remains above the x-axis for all values of x. The y-intercept is always 0, 1, and there is no x-intercept. The y-intercept is 0, 1 because for any base a to the 0 is equal to 1. The x-axis is a horizontal asymptote. So exponential functions will have a horizontal asymptote in the same fashion that certain rational functions had horizontal asymptotes. If the base a is greater than 1, then the function is increasing. We can see that in the graph shown at the right here, f of x or y equals 2 to the x or 3 to the x. You can see that the graphs rise from left to right. On the other hand, if the base is less than 1, such as in the case of y equals 1/2 to the x or y equals 1/3 to the x, the function is decreasing and the graph falls from left to right. Furthermore, for any exponential function, the function is 1 to 1. That means every x gives us a different y value, and the graph will pass the horizontal line test. A horizontal line will intersect the graph at most once. So since any exponential function is 1 to 1, it has an inverse. And this inverse turns out to be a logarithmic function. So the fact that exponential functions are 1 to 1 is very important in establishing a relationship with the other class of functions that we'll look at in this chapter, that is, the logarithmic functions. We'll continue with the section 4.1 notes in the next video.